In this episode, we will illustrate how to calculate the changes in the free energy of substances as a chemical reaction reaches an equilibrium or a chemical reaction occurs in general. And so let's take the reaction nitrogen plus hydrogen to give rise to ammonia. This is a very important industrial chemical reaction where millions of tons of ammonia are produced for fertilizer generation. If we were to balance the chemical equation, we'll quickly notice that we need half a nitrogen molecule and 3/2 of a hydrogen molecules to produce one molecule of ammonia. All reactants and products are in the gas phase. Of course, this is done at an elevated temperature under specific conditions of temperature and pressure, etc. And so the equilibrium constant for this reaction at, let's say, 450 degrees centigrade is given as 6.59 times 10 to the minus 3. Now we are asked now to calculate the standard reaction Gibbs energy for this process. So how do we do this? So we will use the equation 11.42, delta G0 equals to minus RT ln K, expressed in terms of pressure, Kp. This is because we are asked to get Gibbs energy and we are given the equilibrium constant. So the equation that connects those two variables is 11.42. So now by simply substituting the above data, so it's as simple as that. So the critical step in doing this calculation is identifying the proper equation. What is it that we really have to choose in order to solve the problem? And so as I said before, look for the hints, for example, equilibrium constant, temperature, Gibbs energy. So the three different components here, and which equation has all these three together? And so that is 11.42. So a tip I would like to suggest to you guys is to make a list of equations. As you go through each module and each snippet, I would suggest you write them down in your notebook. Equation 1, 2, 3, 4, 5, like that. You may end up as many as 100 equations. Don't worry about that. That's okay. And you don't have to memorize them. Just have a list with you so you can consult the equation when you require to use it. So this saves you a lot of time than to going through the modules or going through the textbook and etc. I do this myself. I have a little list of equations and then I look at them periodically to familiarize myself. I don't memorize them, but to familiarize myself so I can recognize the symbols, under what conditions these are applied, and what conditions these equations do not work, etc., etc. So by doing this periodically, again and again, you will be very comfortable with these equations. I think that's the most important thing. We should be comfortable in using the equations, and that comes through extensive familiarity of these equations. So writing the equation down by hand is one of those situations where you're engaging multiple mental faculties to bear upon the equation. So it settles better in your mind. What is it and how do we apply? Where do we apply? Where we should not apply, and so on and so forth. So delta G0 then equals to minus R. So that is the value of R with its units. T, the temperature in Kelvin, and log of the Kp. Now remember, you can only take a log of a dimensionless quantity. Therefore, the equilibrium constant expressed in pressure here is specifically written dimensionless. And that's how we derived it. You would see that in our derivations. It's a dimensionless quantity. And so then we can comfortably take the log of that, of course, natural log of that, and convert that into log base 10 or whatever you want. It's up to you. And these days, Google can make all this math for you instantaneously, essentially. And so you get the numbers there at the end. So the Kelvin and per Kelvin cancel away, joules per mole. So units are right. And so this is formation energy and therefore free energy, therefore is per mole. We have written that and we got the units right. And it is a positive quantity. What that means is ammonia is not very stable. You need energy to convert nitrogen to ammonia. Otherwise, the nitrogen gas in the atmosphere would have been converted long ago into ammonia. And that is the situation here. It takes certain amount of energy to break the nitrogen molecule into its component atoms and react with the hydrogen to produce ammonia. And so even at this elevated temperature, 450 degrees centigrade, it requires a considerable amount of free energy to produce this product. So this is why these fertilizers are quite expensive, because you need to spend a lot of energy, which costs and to produce this ammonia, and then which is then used to produce other fertilizers from it as well. Nevertheless, so this is a formation free energy, and therefore this is also called as the Gibbs energy formation of ammonia at this temperature. The second example here, 11.2, we're going to look at an equilibrium and analyze the equilibrium concentrations in terms of initial concentrations, mole fractions, degree of advancement, all these terms that we have used previously in the slides. So let's consider this two component equilibrium reaction, dinitrogen tetroxide dissociating in the gas phase to give rise to NO2. So one molecule of N2O4 in the gas phase breaks up to produce two molecules of NO2. It's also in the gas phase. So stoichiometric, the analysis of equilibrium has to be systematic. So here I've shown this step by step. How do you do this? Stoichiometric coefficients. So the reactant N2O4, 1 mole of it reacts, and therefore it's a reactant, so you have a negative sign for the stoichiometric coefficient, -1. NO2 is the product. It builds up as reaction progresses from left to right, and so it has 2 molecules of NO2 is produced. Therefore, the stoichiometric coefficient is +2. The initial mole numbers, you can say N0 for the N2O4, and NO2 is nothing. We start with pure N2O4 and then try to achieve the equilibrium from it. So if that is the case, N0 is the number of moles of N2O4. You start with 0 moles of NO2. The problem may state something different. That is okay. If the problem states initial concentrations of each of the reactants and products, we're going to use those as well. So now, equilibrium mole numbers. So let's say that it took certain time to achieve equilibrium. The degree of advancement is xi sub e, and the equilibrium position. And so one would have obviously consumed N0 minus xi e moles. Xi e moles would have been consumed. So the number of moles of the reactant would be N0, the initial mole numbers, minus xi e. So that is the mole numbers of N2O4 and the equilibrium conditions. Now we would have made twice as much of NO2 as we consumed N2O4. So 2 times xi e will be the number of moles of the product produced at the equilibrium position. So xi e is your equilibrium advancement. We can now calculate mole fractions, because we know now number of moles of reactants, number of moles of products, and so we know total number of moles we have. Therefore, we can write the mole fraction. And so we can now, of course, easily write this out, N0 minus xi e divided by N0 plus xi e. And I have now written the mole fraction for the product, which you can do by yourself. And so I'm skipping that. So I just want to make sure you do that. And using alpha, the degree of dissociation is equal to xi e divided by N0. That's because xi e moles are produced from N0 moles, so at the equilibrium. So that is the degree of dissociation. We can now calculate the mole fraction. And 1 minus, in terms of degree of dissociation, all that means is wherever xi over N0 is present, replace it with alpha equilibrium dissociation. So 1 minus alpha e divided by 1 plus alpha e. That is the mole fraction of the ith component or the first component here in this particular case. Now you can write the mole fraction for the second component in terms of alpha E as well, which I have left out in this particular case. And so partial pressure we can write as P sub I of the ith component equals to mole fraction of the ith component xi multiplied by the total pressure P. So now I can now write the partial pressure of component 1 as 1 minus alpha E over 1 plus alpha E, that is the mole fraction written in terms of degree of dissociation alpha, and for the reactant. Similarly, now you can write the partial pressure for the product, which I have left out, so which you can fill in this particular case using alpha and the total pressure P. So equilibrium now of this reaction is studied by simply measuring the vapor density of the equilibrium mixture, because these are gases decomposing, blah blah blah, all this is happening, and so we can measure the the density of the gas mixture. From that we can calculate the equilibrium constant, etc. Why is that? That's because one molecule is decomposing to give rise to two product molecules. So that means the number of moles are increasing. That means the system, if you were to do it at constant pressure conditions, will have larger volume. So as the volume increases, the density decreases. So it's very simple. So we are assuming it's done under constant pressure conditions, which is the total pressure P. But then if you keep the total pressure P constant, the volume has to change. Okay. All right. So we can do the experiment either way, whichever is convenient. Either keep the volume constant or the pressure constant. All right. So as you continue using the values from the previous equations, that we can now write Kp, the equilibrium constant for the reaction in terms of pressure, the pressure of NO2 squared, partial pressure of NO2 squared, because that's your two molecules of NO2 is being produced, divided by the partial pressure of N2O4. So that is classical general chemistry expression. Using the stoichiometric coefficients, you can write the equilibrium constant. And so now you can write those partial pressures we wrote in the previous slide in terms of alpha, and we substitute them and simplify, square them, simplify, and you get 4 alpha squared times pressure P divided by 1 minus alpha squared. And so of course they're all equilibrium alpha values, which I have not mentioned. So by the ideal gas law, we can now see that the pressure, volume, and the temperature, number of moles are related. And now N is the number of moles in the equilibrium situation, and that is total number of moles is 1 plus alpha times N0, that we see from the previous slide. And so now we can write PV equals to N0 1 plus alpha times RT. So pressure or volume now related to alpha. So this is very useful because now we're going to now substitute all this back in. N0 is simply the number of moles, initial number of moles of the reactant, that is equal to W over M, where W is the mass of the gas in the beginning, in the volume V, and M is the molar mass of N2O4. And so now we can get rid of N0 and write in terms of these other constants as well, right? So from pressure, temperature, volume, and W, these are all measurable quantities in the lab. With the experiment, we can now calculate alpha, and from using the value of alpha, we can calculate Kp. So it will look very circuitous, but this is how the math needs to be worked out. In the lab, we measure pressure, volume, temperature, mass, etc. And we need to calculate equilibrium constant Kp. From that, we can initially we can calculate alpha, then we can calculate Kp, then we can calculate delta G from that. So this is how the experimental work is related to the quantities that we are interested in measuring in the experiment. So by measuring alpha at any pressure, means constant volume conditions, we can then determine Kp. From Kp, calculate delta G for the reaction. And the dependence alpha on pressure is also then can be calculated because we have the pressure explicitly written in the equation 11.52. Alpha equals to Kp by Kp plus 4p under square root. So go back and look at 11.52 to demonstrate the degree of dissociation and Kp are related to each other through the pressure of the system P, total pressure of the system P. So very nice thing about this expression 11.52 is that as pressure goes to 0, yeah, then the denominator becomes Kp. So the numerator and denominator are exactly the same. Cancel away, square root of 1 is 1. So then alpha is 1. Degree of dissociation is 1, means there is a complete dissociation of the system as the pressure drops to 0. As the pressure goes to infinity, of course you get the reverse. That is, there is no dissociation of the system. So there is an explicit dependence of the equilibrium constant on the the dissociation, degree of dissociation on the pressure of the experiment. So this is what you would have expected from the Charlier principle. We have looked at that briefly as well. So at moderate pressures, what happens? At moderate pressures, Kp is quite small compared to 4p at moderate pressures. And so we can neglect Kp in the denominator. Okay? If you neglect the Kp in the denominator, then alpha is equals to square root of Kp over 4p. So again, this is an approximate value, not exact value. So this is how the values can be adjusted as low values, medium values, or high values, and based on that we get different results. Example 11.3 is slightly more elaborate than we have dealt with previously, and this is also quite interesting, and I thought I should show you a little bit. And so consider the reaction N2 plus H2 giving rise to ammonia, same as before, but now we have two molecules of NH3, so we have whole multiples of the stoichiometric coefficients here. So stoichiometric coefficient of nitrogen is -1, hydrogen is -3, ammonia is +2, as we discussed before. And the initial mole numbers are given here. We have, say, a mixture of 1 mole of N2, 3 moles of H2. So 1 mole of N2 and 3 moles of H2 and 0 moles of ammonia. That is the starting point. Okay. So equilibrium mole numbers. Xi is the degree of advancement. Then 1 minus xi will be the mole numbers of nitrogen. 3 minus 3 xi will be the mole numbers of hydrogen. And 2 xi is the mole numbers of ammonia at the equilibrium conditions. Now we can write mole fractions because now we know mole numbers, we know the total mole numbers, and therefore for each of the substances you can write mole fractions. And I would like you to write them down. I have written this explicitly, but I would like you to check them out. Okay. All right. Then the partial pressures can be written. We have discussed this again previously. Xi times P equals to Pi. Therefore, that is that multiply the above rho with pressure for each of these terms. So now what is important to see here as you look at these numbers very carefully, in the last row you will immediately recognize that the pressure of hydrogen is equal to 3 times the pressure of nitrogen. And so this is quite useful in the next step, and so where we write the Kp. So Kp is pressure of ammonia squared divided the pressure of nitrogen multiply the pressure of hydrogen cubed. And so now making the substitution, pressure of hydrogen goes to 3 times the pressure of nitrogen. We now redo the denominator at 3 times pressure of nitrogen cubed. So this now simplifies the situation, and we get the Kp expression is equal to pressure of ammonia squared divided by the 9 times the pressure of nitrogen raised to the power 4. 3 cube is 9. So now let's continue this and we'll be done in a few minutes. And so that is your pressure of ammonia divided by pressure of nitrogen squared. So you can take the square root, you can do the reverse of it. So I rearranged the expression last from the previous slide. So using the partial pressures that we have derived in the previous table, now I can write all those values 3 power 3 half Kp to the power half is equals to these mole fractions that we have written, partial pressures we have written previously. Substituting them in it, you get these numbers, and in terms of xi and in terms of pressure, total pressure P. So the Kp is now explicitly related to the advancement and also the total pressure. So now if we analyze the reaction mixture carefully, we can get the mole fraction of ammonia from which the value of xi at equilibrium is obtained. From xi we can calculate Kp, and from Kp we can calculate delta G0. We can also formulate the expression in terms of pressure of ammonia as well as the total pressure. This is very simply because the pressure total equals to pressure of nitrogen plus pressure of hydrogen plus pressure of ammonia, and pressure of hydrogen is simply equal to 2 times the pressure of nitrogen. And so we can now substitute all those values and then put in the total pressure into the system. And so we can write the pressure of ammonia divided by the P minus P of NH3 squared is equal to this. So from this relation, we can simply calculate the partial pressure of ammonia at any total pressure, so which is what we need, partial pressure of ammonia at any total pressure if you so desire.